Hi, today we will discuss another example of redox reaction, transfer of electron at a distance. In all redox reaction, electrons are transferred from the reducing agent to the oxidizing agent. All of the examples we discussed before involve direct transfer of electron, where the reducing agent and oxidizing agent are mixed together. All involve transfer of electron that occurs quickly, and this transfer of electron cannot be detected. However, when the reducing agent and the oxidizing agent are separated by an electrolyte in a U-tube, as shown in this diagram, the transfer of electron occurs through the connecting wire. The electrolyte used here is dilute sulfuric acid, and this dilute sulfuric acid electrolyte acts as salt bridge to separate reducing agent and oxidizing agent so that the electron is forced to flow through the wire. And the flow of electron through the wire or external circuit can be detected by galvanometer. And deflection of needle of the galvanometer show the direction of electron flow. So now, let's discuss the general rules for transfer of electron at a distance. On the left arm here, we have a reducing agent, and the right arm we have oxidizing agent. So first of all, this reducing agent will undergo oxidation by losing electron. So the electrode at which oxidation occurs is labeled as the negative terminal. From there, the electron will flow through the external circuit to the other electrode, and this other electrode is now known as positive terminal. The transfer of electron or the flow of electron will be detected by the galvanometer. So the third step, the electron will be accepted by the oxidizing agent, and this oxidizing agent will undergo reduction by accepting electron. So let's summarize that. Reducing agent undergo oxidation by losing electron. This electron flow through the circuit, and the oxidizing agent accept the electron and undergo reduction. Before we discuss example of transfer of electron at a distance, let's look at some common reducing agent and oxidizing agent. Some example of reducing agents which will undergo oxidation that involve loss of electron are Fe2 plus ion. So Fe2 plus is green and plus 3 is brown. So for potassium chloride, the color change is Cl minus is colorless while Cl2 is pale yellow. For potassium bromide, Br minus is colorless and Br2 is reddish brown. For potassium iodide, I minus is colorless and iodine is brown. Now let's discuss common oxidizing agent used which will undergo reduction by gaining electron. We have discussed before these three substances, chlorine, bromine, iodine, and all of these involve change in oxidation number from 0 to -1. So decrease in oxidation number, reduction, so act as oxidizing agent. Today I will focus on two oxidizing agents that are rather new to you, which is acidified potassium manganate VII KMnO4 solution and acidified potassium dichromate K2Cr2O7 solution. MnO4 is a manganate ion, and the oxidation number of manganate ion is +7. Cr2O7 is a dichromate ion, and the oxidation number of chromium in dichromate ion is +6, and manganese ion is +2. while chromium ion is +3. The reason why acidified potassium manganate and acidified potassium dichromate are widely used as oxidizing agent is because of the distinctive color change, where manganate ion MnO4-, the color is purple, while manganese ion Mn2+, the color is colorless. So we can easily observe the color change from purple to colorless upon reduction. While the dichromate ion is orange and the chromium ion is green. So we can observe color change from orange to green. We will discuss on how to construct the half equation of reduction for acidified potassium manganate VII solution. From my previous lecture, step 1, 3, 4, and 5 is the common step to write half equation. The only new step here is step 2. And step 2 is only used for acidified potassium manganate VII solution and acidified potassium dichromate 6 solution. Step 2, we add H+ ion in the reactant due to the presence of H+ ion for acidified solution. And the hydrogen ion will also take part in the reaction, forming water as the product. So we add water in the product. So let's begin with step 1. The reactant is manganate ion, MnO4- manganate ion, and the product is manganese ion, Mn2+. So reactant and product, check. Step 2, we need to add H+ ion in reactant and H2O in product. So MnO4- plus H+ produce Mn2+ plus H2O. Step 3, balance atom. So there are 1 manganese in the reactant and 1 manganese in the product. So the manganese is balanced. Next, there are 4 oxygen in the reactant but 1 oxygen in the product. So we will add 4 in front of the water molecules. So that make the hydrogen 4 times 2, 8. So there are 8 hydrogen in the product but 1 hydrogen in the reactant. So we will put 8 as coefficient in front of the H+ ion. Next step, we need to add electron. And since this is a reduction, that involves gain in electron. So when gaining electron, we will write the electron in the reactant. Before we can balance the charge, first we need to determine the net charge in the reactant and the net charge in the product. So manganese ion is -1, 8H+ is +8. So the net charge is +7. On the product side, manganese ion is +2 and water is neutral, so the net charge is +2. So in order for +7 to be equals to +2, we need 5 electrons. So that +7 minus 5, the net charge will also be +2 and is now balanced. Next, we will work on the reduction half equation for acidified potassium dichromate 6 solution. So the reactant is dichromate ion, Cr2O7 2-, and the product is chromium 3+ ion. Step 2, we'll just add H+ in the reactant and water in the product. So Cr2O7 2- plus H+ produce Cr3+ plus H2O. Step 3, we balance the atom. There are 2 chromium in the reactant but 1 in the product. So we put coefficient 2 in the product, and there are 7 oxygen in the reactant but there are 1 oxygen in the product. So we put coefficient 7 in front of H2O. Now there are 14 hydrogen in the product, but 1 hydrogen in the reactant. So we put 14 coefficient in front of H plus ion. Next, we need to add electron. And since this is a reduction process, reduction involves gain of electron. So electron is written on the reactant side of the equation. Now, in order to balance the charge, we need to first determine the net charge in the reactant, net charge in the product. So dichromate ion is -2 and 14H plus is +14, making the net to be +12. 1 Cr is 3 plus, 2 Cr is +6, while water is neutral 0. So in order for +12 to be balanced to become +6, we need to add 6 electron. So that +12 minus 6 is +6, and now the charge is balanced. Now, before we discuss example of reaction to study transfer of electron at a distance, I will work with you to discuss step-by-step process to understand transfer of electron at a distance. So step 1, we will identify the reducing agent and the oxidizing agent that is provided. Step 2, we need to label the electrode as negative terminal or positive terminal. So before we can do that, reducing agent will undergo oxidation, and oxidation involves loss of electron. And since this electrode is deep inside reducing agent, which will lose electron, this electrode is negative terminal. So negative terminal here will indicate which electron the electron came from, and the opposite electrode will then be the positive terminal. Step 3, we will write the half equation of oxidation. Now, the electron lost by reducing agent will flow through the external circuit through connecting wire. And step 4, we need to label the electron flow from RA to OA. And remember to always label the electron flow in the wire and label E. Next, the electron will be accepted by the positive electrode and then accepted by the oxidizing agent. When this oxidizing agent accepts the electron, the oxidizing agent will undergo reduction. And next, we will write the half equation of reduction. By having the half equation of oxidation and half equation of reduction, we can combine those equations to write the overall ionic equation. And last but not least, of course, we need to write the observation in reducing agent and oxidizing agent. Now, let's discuss example 1, reaction between iron to sulfate and acidified potassium manganate 7 solution. So, step 1, we need to identify which reactant act as reducing agent and oxidizing agent. Well, we don't have to memorize the list of oxidizing agent and the list of reducing agent. Let's just work on from the oxidation number. If the ion here is +2, it is very likely that the iron will be oxidized to Fe3+. So that is an oxidation, meaning iron to sulfate will act as reducing agent. So iron to sulfate solution is the reducing agent, and for manganate 7, it's +7 manganate ion will be reduced into manganese +2 ion. So this is a reduction, so that acidified potassium manganate PII solution will act as oxidizing agent. Since the reducing agent will undergo oxidation by losing electron, Electrode deep inside iron to sulfate solution will be the negative terminal, and the opposite electrode will be positive terminal. Step 3, we will write the half equation of oxidation, whereby Fe2 plus become Fe3 plus oxidation, so that is loss of electron, and electron is written on the product side. So this electron that is lost during oxidation will flow through the external circuit, and the electron will be received by the acidified potassium manganate, so that this acidified potassium manganate undergo reduction by gaining electron. The manganate ion is MnO4 minus, and the product is manganese Mn2 plus ion. So step 2, we add H plus in the reactant, and we add H2O in the product. So step 3, we balance the atom. There are 4 oxygen in the reactant and 1 in the product, so we add 4, which make the hydrogen add. So we put add in front of H plus, and now all the atoms are balanced. Step 4, we add electron, and since this is a reduction process, gain of electron is written in the reactant. The reactant is now -1 plus 8, that make it plus 7, and the product is plus 2. So in order for this charge to be balanced, there must be 5 electrons, so it becomes plus 2, and the charge is balanced. Now, in order to obtain the ionic equation, we will need to combine these two half equations. However, the number of electrons released in oxidation half equation and the number of electrons received in half equation of reduction is not the same. So in order to balance that, half equation of oxidation need to be times by 5, so that 5 electron lose become 5 electron gain, so the electron can cancel out each other. So now we'll just write the whole equation. 5Fe2 plus MnO4 minus plus 8H plus produce 5Fe3 plus Mn2 plus 4H2O. So that is the complete ionic equation. So our last step is the observation in reducing agent and observation in oxidizing agent. Fe2 plus is green, while Fe3 plus is brown. So we'll observe the colors change from green to brown. Next, for acidified potassium, manganate ion plus 7 is purple, while the manganese ion plus 2 is colorless. So we'll observe the color change, purple to colorless. Now, in order to confirm the identity of product formed on the reducing agent, 2 cm cube of the iron to sulfate solution is taken by using a dropper, and then a few drops of potassium thiocyanate solution is added, and we will observe a blood red coloration. This blood red coloration indicates the presence of ion 3 ions. Next example, we will discuss the reaction between potassium iodide solution and acidified potassium dichromate VI solution. So first step, acidified potassium dichromate acts as oxidizing agent, and potassium iodide will act as reducing agent. This reducing agent, which is potassium iodide, will undergo oxidation by losing electron. Since P is where the electron came from, P is the negative terminal. Q is automatically become positive terminal. Now, the third step, we need to write the half equation of oxidation. So potassium iodide, I minus ion, become iodine, I2. And this is an oxidation process, and oxidation occurs by loss of electron. And when we lose electron we write on the product side, so plus electron. Next step, we balance the atom, I2, so 2I minus, and if 2I minus, it's also 2 electron on the product. Electron will now flow through the external circuit. The electron will always flow from reducing agent to oxidizing agent, because reducing agent lose electron and oxidizing agent gain electron. So this electron will be accepted or gained by potassium dichromate solution, which then undergo reduction. And so now we will write the half equation of reduction for acidified potassium dichromate 6 solution. And we have discussed this in previous slide, but I will do it again here very quickly. So the dichromate ion is Cr2O7 2 minus, and the product is chromium 3 plus ion. Step 2, we need to add H plus in the reactant, because this is an acidified solution, and the H plus ion react to form water in the product. So now let's balance the equation. There are 2 chromium in dichromate ion, but only 1 chromium on the product, so we add coefficient 2. There are 7 oxygen in the reactant, but only 1 oxygen in the product, so we add 7 coefficient in front of H2O. Now the hydrogen in the product become 14, 7 times 2, 14, but there's only 1 hydrogen in the reactant, so we add 14 coefficient in front of H plus ion. So now the atoms are balanced. Next, we need to balance the charge by adding electron, and since this is a reduction process, reduction occurs by gaining electron, so the electron is written on the reactant side. Next, we need to balance the charge. So on the reactant side, chromate is minus 2. There are 14 H plus ion, so that is plus 14. The net is plus 12. While in the product, there are 2 chromium, so 2 times 3 is plus 6. So because of that, we need to add 6 electron, become minus 6, so that the net charge become plus 6 also, and balance. Next step, the half equation of oxidation and half equation of reduction are combined to produce the overall ionic equation. Since the number of electrons on both equation is not the same, so first the half equation of oxidation is multiplied by 3, so becomes 6 electron lose during oxidation and 6 electron gain during reduction, so that both electron can be cancelled out. Next, we just write what is left on the equation, where product of oxidation plus product of reduction, reactant of oxidation plus reactant of reduction. So there are 6 I minus plus Cr2 O7 2 minus plus 14H plus 3 iodine plus 2 Cr3 plus 7 H2O. So the last step will be the observation on the reducing agent side and oxidizing agent side of the U-tube. In the reducing agent side, the color of iodide ion is colorless, and this iodide ion is oxidized into iodine, which is brown. So the color change is from colorless to brown. For potassium dichromate, the color of dichromate ion is orange, while the color of chromium ion plus 3 is green, so that the color change is from orange to green. We will also perform confirmatory tests for the product that form on the reducing agent side of the U-tube. So by using a dropper, 2 cm cube of potassium iodide solution is taken and put inside a test tube. Then a few drops of 1% starch solution is added to the test tube, which will produce dark blue coloration. And this dark blue coloration confirms the presence of iodine and successful conversion of iodide ion into iodine. So to summarize what we learned today, step 1, we identify the reducing agent and the oxidizing agent, and the electrode deep inside the reducing agent is negative terminal, and the electrode deep in oxidizing agent is the positive terminal, and the electron will flow through the external circuit from reducing agent to oxidizing agent. And then the electron will be accepted by oxidizing agent, which undergo reduction by gaining the electron. So that is the end of our lecture today. Thank you very much for your attention, and remember to stay home